So we're delighted to have Elke Scheer. So changing the topics depending on the workshop topic. So thank you very much, and yeah, the floor is yours.
Yeah, thank you for the invitation. Sorry, I decided to change topic based on discussions that were ongoing. Basically, motivated by the talk of Moed Randeria on Monday. I think he's now not here anymore. But anyway, I hope you will enjoy. So, so it is about parity breaking and symmetry breaking in general, and also the question how to probe this by tunnel spectroscopy. NCS means non-centrosymmetric superconductivity, and my background is basically coming from signatures of triplet superconductivity in hybrid devices, and here we think we have evidence for that in a three-dimensional system. It's even not two-dimensional what I'm talking about. Probably discuss about circumstances. Okay, so as I said, After is finding indications for pairing symmetries, and we all know that, let's say, according to Pauli's exclusion principle, the total wave function must be odd for a fermionic system, but there are different combinations possible. We have the momentum degree of freedom, the spin, and also the time of frequency degree of freedom. And depending on that, we can also have triplets. And the question is, what do which symmetries are suitable to break to have a sizable triplet component in the order parameter? Yeah, and the system that we are investigating is a bulk, a three-dimensional but non-centrosymmetric superconductor. So if we are in a symmetric system, then we can decide whether it is even or odd. But when we are non-centrosymmetric, we cannot apply this symmetry anymore. So parity is not a good quantum number. And as a result, there will always be parity. There will always be parity mixing, and not a single parity or sharp parity of the order parameter. And so this is the reasoning in short how it works. So if we have a crystal that lacks inversion symmetry, then there are always internal electric fields which act on the atomic length scale, and they give rise to internal momentum-dependent magnetic fields, and as a result, there will be Rashba-type and isotropic spin orbital count. Then it depends on how big this is and if this is a sizable effect. How does it work in more detail? The canonical pairing symmetry in a non-centrosymmetric superconductor is that one has these spin flip Fermi surface which is split, and then if you go through the math with these outline that I gave before, one always has a two-component order parameter that has an even parity scalar component and an odd parity vector function. And if you project this on the spin space, you will see that you have always contributions of singlet components and triplet components. This is the general symmetry consequence of this symmetry breaking. And we are not the always a bit with delay. We are not the only ones, or the first ones who are investigating this. In fact, in the heavy fermion community, this has been investigated already more than 20 years ago, and the prototype system where this has been shown first is cerium platinum 3 silicon, where the first evidence came from NMR studies, so this longitudinal relaxation time study where it has been found that there is a coexistence of an antiferromagnetic and a superconducting phase, and that this could be described with a triplet components or p-wave components in the order parameter. There are several other examples, and when you go through the literature, you find that basically you find evidence for such physics when you're in strong correlated systems. So as I mentioned, so this heavy fermion system, cerium, platinum, silicon was the first one. There are also studies on this and this is a system where the superconducting ordering is supposed to be non-phononic, but based on antiferrometric fluctuations. And there are also studies in this system here, which is a phonon-coupled superconductor. And there are also some indications for asymmetric spin-orbit coupling, which gives rise to indications for this parity-broken order parameter. But there, in the literature, there are also many examples where, despite having this strong spin-orbit coupling, there are no indications for triplet superconductivity. Everything can be described with S-wave symmetry. So the question that is open is it always necessary to have these strong electronic correlations, which are present in heavy fermions, and the spin-orbit coupling to have triplets, or would it also be possible to have this triplet components and broken, so parity mixed order parameter with the spin-orbit coupling alone? So we are looking for a system that has these strong spin-orbit coupling, but not strong electronics coupling systems. And so this is, well, as I said, the first question. And what's going on here? And the second question is, can we learn something with STM or tunnel spectroscopy measurements on the symmetry of the orbital? So the system that we're investigating, our star, is niobium-rhenium. Niobium-rhenium is a compound which, in a certain ratio of niobium mixture into rhenium, crystallizes in a very particular crystal structure, which is the alpha manganese structure, a very complex one with 58 atoms in the unit cell. And depending on the stoichiometry, the superconducting transition temperature changes. This is shown here. So resistivity measurements a function of temperature for different compounds. And the one here shown in black, this is the one with 18% niobium, which is exactly this stoichiometric compound that is shown here, and the one that we are investigating, which has the sharpest transition and also the highest TC. And also here, we are not the first ones who investigated this system. So there's quite some literature starting probably 10 or 15 years ago, where people were searching for this order parameter symmetry, and there are conflicting results. Some papers suggest it's S-wave. Some papers suggest that there is a time reversal symmetry breaking, and also evidence for intrinsic triplet superconductivity. So the question is open: what is really the order parameter? And this is probably for the people who are working in these quantum material and correlated electron systems. So when we plug in and test for indications for electronic order, we are in the situation for weakly correlated maps. So we don't have strong electronic correlations. Okay. When it comes to transport measurements, there is a group of Carla Cirillo and Salerno who investigate the systems quite intensively. And what she found is that if she uses point contact spectroscopy on single crystals, so not atomic point contacts, but let's say 10 nanometer size point contacts, she finds indications for two gaps, but S-wave with S-wave symmetry. While when she's studying extended crossbar tunnel junctions, then it all looks like a single S-wave, a bit rounded, but it's all consistent with assuming a single order parameter which would have isotropic order. So we need spatially resolved measurements to address this question. And so this is now our experiment. We are doing STM at low temperature. We're using a normal tip, platinum iridium, and then and this works at 300 millikelvin. And then we probe the tunnel spectra to learn something about the order parameter symmetry. So the typical concept that one has in STS for investigating superconductors. And the hope is that we find the fingerprints of the K-space symmetry of the order parameter. When it's S-wave, then we expect to see these fully gapped spectra. When they have somehow anisotropic S-wave, so still S-wave, but with some modulation of the amplitude, we would expect still something that is fully gapped, but with some modulation in the shape of the spectra, while when we have nodal lines, then we will have in-gap states, and then depending on the order parameter symmetry, D wave or P wave, the shape inside the gap would be different. So this is our approach. So we started with thin films of niobium rhenium, thickness typically 20 nanometers, roughness about 1 nanometer. And what we see there for most spots is a fully gapped spectrum, so compatible with BCS. You see here that there's a temperature dependence that is shown here, and deducing the gap with the DINES model. We need a very small DINES parameter, but it can be reasonably well described by BCS. And also when we study them in magnetic field, perpendicular magnetic field, I should say, it can describe as a BCS fit, and the pair breaking, the optical pair breaking, is accounted for also by a DINES parameter. However, this is not the only possibility of spectra that we can have. There are also statistically really significantly spots where we see deviations from this S-wave geometry. And here you see a selection out of many spectra that we took. So there are more rounded spectra that are not fully gapped anymore, so not flat inside the gap, with some V-shaped characters. We can have in-gap states, and also something that looks really like P-wave, or let's say these V-shaped, V-shaped. We have double peaks, and we can follow them also as a function of magnetic field. There's one example of one of these more or less V-shaped. The experimental data are the data points. This is 0 Tesla. The orange curve is the best fit, assuming an S-wave, a single S-wave order parameter. You see it doesn't work, and it is already much better when we assume a superposition of an S-wave and an E-wave. And then when we apply magnetic field, we do see that the gap is filled, and we can do this also for different spectra. And what is shown here on the right-hand side are two examples of the development of the gap, or let's say not the gap, I should say, but the zero bias conductance as a function of magnetic field. The dashed curve is what we would expect by Markey theory, so assuming the Zeeman spin splitting, and the blue curve is what we observe experimentally for our fully gapped spectra. And the gray curves is what we see when we have these V-shaped spectra. And so these are cartoons explaining this behavior. So as soon as one has low-lying excitations, then of course, and you apply a magnetic field, then you will fill up the gap very fast. So this is all indications for that we do have an order parameter symmetry that is not simply S-wave. However, we have this mixture, we have these granular films where we might have different orientations that we are probing. So to learn more about what is going on, we then went to single crystals, and we probed the single crystals in different crystalline orientations. And the 4 planes that we're probing, they're shown here in this graph. So we were probing in the ground plane, the 001 plane. We were probing in this the diagonal plane 110, and then also two other ones which are a bit, let's say, not parallel to any crystalline axis. The 2 minus 1, 2, this is shown in yellow here, and the 113, which is shown in blue. And why were we probing these directions? First of all, we got crystals with surfaces from the group of Gisa Balakrishnan and Michael Smigman. And they had some of these surfaces, 001 and the 113, and the other ones we generated by polishing them on a certain angle. And we have chosen these other planes on purpose to probe hypothesis on the order parameter symmetry. So let me start by the two boring planes. These are the 001 and the 113. Measured by EBSD, so that these are really these planes. And what we do see there is basically fully gapped BCS that can again be described with a DINES parameter, typical gap size, a millivolt, which corresponds also to the TC that I did not mention, that is 8 point something Kelvin in our case. Now, when we do the spectra, let's say on the 1-1 plane, we do again see this variation of spectra that we saw also on the thin film. So we can have fully gapped, we can have these, let's say, still a gap, but with a kink. We can have these double peaks and these more V-shaped in the center. And we have quite some statistics that these are the typical spectra or classes of spectra that we do see. Also here we can follow one of them, for instance, one which is a bit like that one here as a function of magnetic field. And here also we do see how the gap is filled and the zero bias conductance increases. And another feature or another test that we can do on the single crystals is comparing how the gap fills when we apply the magnetic field perpendicular or parallel to the plane. And here we see a sharp difference. So the dashed curve would be the one that we measure at zero field. So it is close to this fully gapped one, so the boring one, if you wish. And then when we apply a magnetic field parallel, this is in blue, or perpendicular to the plane, the gap filling is different. And these are all hints for anisotropic order parameter and consistent with a two-component order parameter, an S-wave-like, and also something that is not S-wave-like. Finally, the last plane, this 110 plane, showed features that exist only on that plane. And this is something that looks like double gaps, right? So here, this is marked with these vertical lines, where we do see shoulders or even peaks, and where the outer peak, if you want to call it the coherence peak, is your choice, is not at 1, as our typical gap is, but it's more like 2 millivolt. And so this is the spectroscopic zoo that we have to understand. And so we asked our theory colleagues, in particular Manfred Siegrist, for help. And what do we know about the material? We know that it is this, we know to which space group and point group the material belongs. We also know that we have antisymmetric spin-orbit coupling. And then we asked him to tell us which gap functions are possible given that symmetry. We know what we measure in the spectra, and the goal is to figure out what is the order parameter symmetry that is in agreement with the symmetry constraints given by the crystal structure and our experimental findings. And so now it becomes very busy. I'm very sorry. The possible basis functions are given here. So the even parity basis functions compatible with the crystal symmetry, only 3. The odd components are 5. And the even ones are shown here. So there could be a spherical one. There can be this DZ2 one. There can be this x squared, y squared. So different possibilities for the even ones. And for the odd ones, they have p-wave characters. And depending on, and all these donut-like parities are still possible. What is shown, and we know this odd component is a vector component, right? And this is why you see here all these vectors. So this is a representation of the vectorial component. Okay, so this is the input that we have, and then we have to calculate what we would expect for the order parameter. And so this is cartooned in this image here. One important assumption that we make here is that we assume a spherical Fermi surface. And then we take these irreproducible gap functions, project them on the Fermi surface, and then calculate the resulting order parameter. And the two ones that I show here are the ones that at the end gave us the best agreement with the experiment. But we tested, of course, all combinations of this zoo that I've shown in the table before. And then we combine these two components to calculate a total order parameter, which then in our case looks like that. So it's it contains this dz square component and this donut-like, it was called gamma 3 in the notation for component. Yeah, and then the question is, what do we measure in our tunneling spectra? And so out of these symmetries, we then have to calculate which projection of the we would see when we probe the density of states. And there now comes in, so that depending on the direction in which we are probing, we can expect either, well, these are now two cuts that have been calculated for two out of these four planes, the 113 plane, which was a innocent one, so to say, and the 110 plane, which was an interesting one, the one that showed the double gap signatures. And what I should say here is the model that we're using is that we are dominantly probing the k vectors in the plane. And this is not an assumption that we put in, but this is something that came out. So we only could describe the whole wealth of our findings when we were assuming that. And this is something I would like to discuss with Tristan, for instance, and others. And I'll come back to that. And this is a model that is usually used for two-dimensional systems, where it comes from. And it works here also in our three-dimensional system. Okay, and then when you do this, we can at first calculate. So by this superposition of the dz squared and the toroidal orbital, what spectra we would expect for the different planes, the 0, 0, 1, 1, 1, 3, 2, minus 2, 1, 1, 1, 0. And here you see that basically we see the shapes that we also see in the experiments, fully gapped ones or ones with kinks here in the slope, and also these double peaks where we have also then coherence peaks which appear at twice the gap. So this is the theory part, and then we can compare this with our experimental findings. And here I only show you one example for this 110 direction. We saw these double structures. And basically, so what the pattern there is that we have a cut through the order parameter, which has two large loops, which have an extension of 2 here in these units, and 1 in the perpendicular direction. And it's basically the superposition of these two extremal lobes, which then can explain also these two peak positions. So, and we can also try to fit. This is done here on this slide here for the 110 plane, exactly what I just showed. You see it's not a perfect fit, but it's a reasonable agreement. It's just as an example, also on this 2 minus 2 plane, where we saw the interesting spectra, we also can describe qualitatively the zoo that we do see. And I should make one remark. So the assumption that we made is that the total order parameter can be described by the square root of this even component on the scalar wave function squared plus the odd component projected on this vectorial component squared. And there is a simplification. We neglected all interference terms. Yeah, and if you do then the analysis, what we find is that the whole zoo again of our spectra can be described with ratios between these odds, which is a triplet component, and the even, which is a singlet component, which is in the order of 40% with some variation between 30 and 45 or so. But it's quite a sizable component. It's not this tiny admixture; it's really a large contribution. Yeah. So now, can we explain this based on the band structure of the system? For that, we teamed up with Carsten Hell's group from Wien and his postdoc Andres Morianuk, who used this Vienna ab initio simulation program to calculate the band structure. And as you see, it's heavily complicated. We have a total of 8 bands crossing the Fermi energy. Luckily, 2 of them are by far the dominating ones, and the other ones have smaller contributions. And then if you look in more details, one of them appears more reddish, right? And the color code here is a Fermi velocity, and small and red is small Fermi velocity. And here our argument is that black bands have more states, so we assume that this band is the one that dominates. And what we also learned from this analysis is, that the Fermi velocity is in the order of 10 to the 5 meter per second, and the size of the spin, this anisotropic spin orbit coupling is really large in the range of 100 millivolts. So we have strong spin orbit coupling. Now again, let's say a slide to set this into the field of other systems that have been observed or have been discussed in terms of having a sizable triplet component. So what one has to discuss there, or what is usually discussed, is what is called ER here in this table. And this is the ratio between the spin orbit coupling and the critical temperature. And in our case, this is 130. And if you look here in the literature, so this again, this Syrian platinum silicon, this is the one that is, well, known as being a triplet superconductor. It has a much larger ER, 3000. Lithium is the one that is also discussed, has 900. And here for these ones here, bismuth, palladium, lanthanum, nickel, the literature is not clear, but it's clear that one needs two gaps or mixtures of parities. It's for sure not a simple S wave. Yeah, we are more or less here in that ballpark, so it would fit to what has been studied before. Yeah, for me, the most important open question is why? Well, all this analysis was based on the assumption that we have preferentially tunneling into the surface, and why do we see that? And so there are also arguments in the literature. There are theories basically made for these cuprate superconductors, where there are theories explaining based on conservation of the momentum in the plane, that one would preferentially probe these components, but they are not really made for three-dimensional systems. And here you see the word topological with a question mark. It has also been suggested by our theory colleagues that probably we are not probing the bulk, but that instead we would be probing topological surface states. I must say I don't believe in that explanation, because after all, our surfaces, they are polished, they are rough. We didn't do any effort to create topological surface states, but it's still something that one could discuss on. And there's also studies on non-centrosymmetric superconductors, where they use basically the same tunneling model that we suggested, but it's also not so, let's say, I didn't understand the explanation, let's say it like that, and we want to discuss with the colleagues as well to figure out what is behind it. Okay, so this is my last slide. The summary. So I think I showed you that we have in this non-centrosymmetric recoupling superconductor sizable parity mixing. We have a suggestion what the mixing and the order parameter. Of course, then this material, if it has these interesting triplet components, could also be good for applications in superspintronics devices. So devices that take advantage of the superconductivity and carrying spin currents. And there are already some examples where the material has been used. Okay, and I forgot to say in the beginning that all the work has been done by Marcel Strohmeyer, a PhD student, and co-supervised by Angelo Di Bernardo and myself at Constance. And we profited a lot from the SEAM collaborations that I mentioned. We received the samples from Lisa Baladrishnan's group, and we are very, very grateful to Manfred Siegrist, who shared all his notes and symmetry arguments with us. Yeah, and thank you for your attention.
So, thanks for this thing. I was wondering, why don't you see some edge state? Because if you have some sign changing other parameters, you expect to have some on states and stuff like that, like rates. Yeah.
We also have examples of that, but they're statistically not very abundant. We do have them, and currently I don't have the numbers at the top of my head. But we may have also, in particular on this surface here, this 1&0 surface, also zero bias anomalies or split zero bias anomalies. And probably something that I should say is each individual spectrum we could probably also fit with another model. Yeah. But the whole bunch we only came up with that solution that I suggested.
Short question. How do you select all your annotations because you have many different facets?
Yeah, as I said, so we got two crystals from our collaborators, which had surfaces, right? And so we were first using simply the crystals as we had them. We did some argon milling to clean, but then we took the surfaces that we had. And then we had already a conjecture of what the symmetry could be. And then we were choosing directions which could be decisive and could give us really information on give us different cuts through this order parameter symmetry. And then also you see how we did it, right? We really polished them manually, right? Or let's say not really manually, but we glued them on a sample holder, and basically this 1,2 minus 1,2 was not what we intended. I think we wanted to have 2,1,3 or so, and this is what came out from analysis. And after all, it was a good choice. It was also a bit of luck to find the good directions.
But the direction don't necessarily on some crystalline directions.
No. So the crystalline, let's say, it is a heavily complicated crystal structure with 58 atoms. And the only one which is parallel to the cubic crystal structure is this 001, and then this 110 you would probably also say, okay, it has kind of symmetry, but let's say there are no simple symmetry axes. So when we say central symmetry is broken, with 58 atoms, it could be only one side that is symmetry broke, but in fact it is not. There are only the niobium sides here on the corner and the one in the center, which see a symmetric Wyckoff environment. And all the others, the 56 others, they really have broken symmetry. So symmetry is heavily broken, and I think this is the advantage of that issue here in this compound.
That was the question with that.
Okay, you were talking about the momentum selection rules and saying that the tunneling favors case within the plane. So maybe you can say a bit more about it. There's something that you can understand post-factum why it happens, or is there any reason that this seems like a very three-dimensional experiment? So why could the selection rules seem to be so two-dimensional?
Yeah, this model has been put forward for planar junctions, and basically to explain that if you have a Fermi surface mismatch, that then the directional angle could be spread up. And here we also have the situation that the Fermi surface Fermi energy of platinum iridium is much larger than the one of niobium. And so we are also in the situation that we have two different diameters of the Fermi surface, if you wish. And this could explain that why, instead of having this usual Terzov modeling, which is directional to the current, we would spread the cone. And this, I think, is very well established in the theory. It does not explain why we have a preference really for the in-plane moments. And this is still something that we would love to understand.
So I'll exploit one short extra question. Is there any degree of freedom in changing the tip that could actually change this selection using iridium, right?
Yeah, it's platinum iridium, and we tested, of course, with different tips, but they were all platinum iridium. Yeah, probably we should try with another metal, tungsten or so. This is a good point. We haven't done this. So usually we do this with platinum iridium. And also we know our tips are not ultra sharp, so we are not really atomically sharp. We don't have atomic resolution. They are kind of blunt, so we have a bit of widening of the tip already. This is what we know. And this is good because we have very stable tunneling conditions then. Yeah, a detailed model is missing. So I really hope that if I discuss with Matthias and look more in detail in that paper, I will understand better. So this is one thing, and sorry, Christoph, one more sentence. Another crucial assumption that we made is that we have a spherical Fermi surface. We know it is not. And this is something that we're now also discussing with our field colleagues, whether assuming an odd order, say a symmetric order parameter, and this very complicated Fermi surface would give rise to similar results. The first tests that we did were not favorable, but I cannot completely exclude.
Maybe one last short question, and then we'll move questions to coffee.
Well, two short questions, you can choose which one to answer.
Okay.
First is, do you know anything about the texture of your films? Are there preferred directions? And second question, do you understand the magnetic field behavior that you observe?
Okay, so about the films, the films are granular. I think I didn't mention it. Grain size is in the order of 5 to 10 nanometers. And our assumption why we do see these different spectroscopic signatures on one film is that we have grains in different orientation. But we did not really probe. So we try to do some XRD, and we know that people preferred a growth direction, but that's all that what we can say. And then the magnetic field dependence, I showed several ones. So which is the one that you're interested in?
Yeah, I remember the one parallel to the surface and perpendicular.
Yeah, this was, yeah, not in detail. So I just wanted to allude to the fact that it's different in these two directions. And this, I think, is a signature that we have some intrinsic anisotropy. It was the very same position, the same spectrum, and also without magnetic field, it went back to the same. So I think it was a stable thing. Still, the development in the magnetic field was different. And so for me, it's just a signature that there is something anisotropic going on. I didn't want to say more about that.